I'd like to introduce our guest speaker tonight. For those of you who have, like I said, sat in on any of Bill's presentations, they're absolutely wonderful. Bill's a very engaging, entertaining speaker. Bill is a retired software engineer, a computer software engineer who's been studying astronomy for over 65 years. His favorite thing to do is teach astronomy to the public, especially children. He's been doing that for more or less continuously over 40 years. He now does it at the Houston area schools and community centers, and he used to do it in Chicago quite a bit. He says the pay is excellent in the form of great questions from the students. And so hopefully we can continue to provide payment with more great questions at the end of the presentation tonight. So without further ado, it's my great pleasure to introduce our guest speaker tonight, Mr. Bill Spizzirri.
Thank you very much, Joe. Shall I share?
Please do so. I'll stop the share here. And the floor is yours. And while you're bringing the share up, I just wanted to remind everybody that if you do have questions for Bill, please feel free to use the chat feature that we have in Zoom and ask away. So we'll get to those in the order that they're received at the end of the presentation. And for those of you who are watching on the live stream on Facebook, you can ask your questions there in the Facebook stream as well, and we'll try to get to those as well. So Bill, it's all yours.
Okay, thank you very much for that intro, Joe. I appreciate it. Presentation, as Joe mentioned, I've been studying astronomy for over 65 years, and because I've studied it so long, people ask me questions, but the big question that I normally get is why? Why would I study anything that long? And there are many reasons. I remember the first time I saw Saturn through a telescope. I remember looking in the Encyclopedia Britannica for the definition of universe. You young folks look at Google encyclopedia. Anyway, and I was surprised when I looked up universe in the encyclopedia, and that was the first time I learned about the expansion of the universe. I was about 10 years old. My brother liked astronomy. He was older than me, so he was cool, so I wanted to do it. My mom bought me every astronomy book there was. But many, many years ago, 45 years ago or so, I learned one particular thing about astronomy that just grabbed my attention. And so that's what I'm going to talk about tonight. And that's just one big reason why I've studied astronomy so long. Now, the title of my presentation, as you see there, is called Bloodlines. That is a term mostly used in genealogy. It has to do with your physical history. Where do you physically come from, your physical ancestry? And we're going to be talking about that. And I normally give this presentation live in person. I was sure hoping we could do that this month, but we'll see how that goes. But anyway, when I'm doing it in person, I always tell the people, hey, I'm going to ask you to do some audience participation. And even though we're Zooming here, I would ask you to try to do the audience participation. And that is to look at the person you're with, if you are with someone, or if not, try to imagine. And specifically look at the eyes of the person with you, not the colored part of the eye or the black pupil, but look at the white part of the eye. And I'll bet you a shiny dime that when you look at the white part of the eye, you're going to see some red lines in that part of the eye. I don't care if it's a man or woman, young or old, where you're from, you're going to have those red lines in the white part of your eye. And then I asked the audience members, I'm certain that we're all seeing those red lines, what are those red lines? And of course, they all raise their hand and say they're veins and arteries. And it's certainly true that there are veins and arteries there, but they are so small. Oh, by the way, I'm not pressing my buttons. There we go. There's an example of those red lines, okay? So there are veins and arteries there, but they're so small, they're so thin that they're transparent. And so what you're seeing is not the arteries, but what's in the arteries. And here's a picture of that. Those arteries are called capillaries. They're very, very tiny. As you can see in this image, they're transparent. And what you're seeing inside is the blood. Now, people think of blood as a liquid. There certainly is a lot of liquid there. If you cut yourself, it obviously looks like a liquid. But there's also, besides the liquid, there's living tissue in your blood. In this case here, you see those little red discs. Those are commonly referred to as red blood cells. Here's another picture of them. The medical term is erythrocytes, but they're cleverly named red blood cells. And I don't know if you can see this on my picture. a hematologist gave me this model of a red blood cell that I can use in my presentation. And as you can see, it's a disc and it's concave on both sides. And that's what a red blood cell look like. And you can see that in the picture. Okay, so when you were looking in the eye and you saw the red, you were seeing theirs. So now we've answered the question, except that begs the next question, why are they red? Okay, well, they're red because every single one of these things, and there's trillions of them in your body, I suppose, they're filled with a molecule called hemoglobin. Okay, now you probably know what a molecule is. It's a group of atoms in a particular structure. Water is a molecule. It's called H2O because it has one atom of oxygen, two atoms of hydrogen. H2O, it's a molecule with three atoms. Hemoglobin, on the other hand, is a protein, a very large and complicated molecule. It has approximately, give or take, 10,000 atoms. Okay, it's a big, complicated molecule. Here's a diagram of it. You can see that it has like 4 sections. You see the 2 pink sections and the 2 blue sections. And in each of those 4 sections, there's the heart of that section called a heme, hence the name hemoglobin. And here's another diagram of it. You can see the 4 sections. The white sections are the hemes within the 4 components of hemoglobin. And here's a close-up of one of the hemes. And in the center of the heme, you see a single orange atom with the Fe next to it. That's an atom of iron. And then you'll see these oxygen atom connected with that orange iron atom. And so when you saw the red in the red blood cells in the eye, you were looking at this iron and oxygen connected to each other. And you might say, hey, Bill, what are you talking about? We know iron is a gray metal and oxygen is a clear gas. What do you mean red? Well, yeah, they are red. And you've seen that before. Here's a picture of a steel bolt. Got a lot of iron in it. It's mostly iron. This particular bolt sat outside for decades, subject to the rain and the water vapor in the air. That water from those 2 sources mixes with the iron on the surface of the bolt. It gets rusty and the rust is red. So that's what it looks like when iron mixes with water. It turns red. And if that sounds strange to you, to imagine that, here's a friend of mine, my son, the scuba diver, took this picture. This is a cleverly named blue crab. And the blue crab has blood, and the blood in the blue crab has hemoglobin. But instead of iron mixing with oxygen in the blood of the blue crab, it has copper mixing with oxygen. And that color might be familiar with you if you ever saw a penny that had been left outside for years and years. It kind of turns a blue-green when the copper mixes with the oxygen in the water, in the outside, in the elements. And here's something you don't see every day. Here's a bottle of crab blood. I forget why they were experimenting with it, but anyway, so we have iron that mixes with oxygen, our blood is red. Crabs have copper in their hemoglobin, and it turns blue. So the next question is, we've answered some questions here, but we go on with the very next question, and that is, how the heck did we get iron in our body? Okay, well, unless you got a special treatment from your doctor, all the iron you get in your body is from the food you eat, period. That's the only place you're going to get it, okay? And so that's where we get it. And all the food, believe it or not, all the iron we get from food comes from vegetation. And you might say, hey, Bill, I'm a carnivore. I eat meat all the time. Or maybe I eat no vegetables at all. But I can assure you, if you do eat meat all the time, all those animals you're eating, the beef and the chicken, et cetera, they all eat vegetation in one form or another, and that's where they get their iron. So that's where you get your iron too. It all comes from vegetation. Oh, and as a matter of fact, take a look at the ingredients lists on some foods, and you're going to see all kinds of elements, okay? Sodium, calcium, zinc, magnesium, things maybe you didn't think you were eating. You see that orange stripe there is iron. It's in the food. As a matter of fact, here's an experiment. If you don't believe me, you take a box of cereal. I would recommend a box of Total. You put it in a blender with some water. You turn it into mush. You put all that in a plastic bag. get yourself a nice, powerful magnet, which I did with my two grandchildren here, and you wipe the magnet around on the outside of the bag, and you're going to actually see iron filings. So is there any iron in our food? Heck yeah. It's so big you can see it. All right. And so we get iron from our food, and our food is all ultimately vegetation. And so there is an example of vegetation, a fruit coming from a tree. But then again, where does the tree get the iron from? Well, if you take a look at the picture, you can see that the tree only gets its iron from one place, and that is the ground. And we have another word for that, ground, and that's called planet Earth. Oh, and by the way, if right about now you're wondering, Bill, I thought this was an astronomy club presentation. We're getting to the astronomy, okay? Trust me. So all of our iron that's in our body that you saw in the eye comes from the Earth. And the question is, how the heck did iron get in the Earth? Well, to answer that question, we have to go back before the Earth was created, before all the planets were created, before the sun and the solar system was created, all the way back, or before all the stars were created, to the beginning of the universe, the Big Bang, 3.8 billion years ago. A big, I'll use the term loosely, explosion of energy that had 3.8 billion years ago. And we won't be talking about what caused it or what came before it or anything like that. We're just going to say that it happened. And when that happened 3.8 billion years ago, the entire universe was in a very small physical area, and it was very, very hot. It was so hot, it was too hot for atoms. All right. A couple 100,000 years, well, the universe immediately, as you can see in this amazing graphic here, the universe started to expand immediately and still does today. And what's normal with expansion in general is as it expanded, it cooled. And after about a couple 100,000 years of expansion, it was cool enough to have atoms. However, there was no atoms of iron. All the atoms at the beginning of the universe was hydrogen and helium and a few other small amounts of trace elements, if you will, of other things, but mostly hydrogen and helium. And so at that point, the entire universe was just, I didn't get rid of the tools up inside. Anyway, it says there that the universe was just big clouds of gas and space, and almost all hydrogen and helium, okay? And let's see here, mostly hydrogen only. So they were giant clouds of hydrogen, and that may not sound like anything very substantial, but we're talking about clouds that are thousands, maybe millions of times bigger than our entire solar system, which means there's a lot of atoms, which means they have a lot of mass, which means they have so much mass that they have a serious gravitational field. And so, when you drop something on Earth, where does it head towards? It heads towards the center of the Earth. We call that falling, right? Heads towards the center of the Earth. The same thing happened in these clouds. All the material of these clouds started to fall towards the center of the cloud. The cloud started to collapse. And as it collapses due to gravity, the pressure increases. And as the pressure increases, the temperature increases. And here's a little video, I think, where you can actually, this is a computer simulation that shows that actually happening, okay? Giant clouds of gas rotating and collapsing towards the center, okay? And so as the pressure increases, the temperature increases, and when it hits to about, give or take 10 or 15 million degrees, then nuclear fusion starts, and that's the first stars, okay? Nuclear fusion happens to be, in these stars, you're going to see how, I'm going to show you now how these stars create things like carbon, helium, nitrogen, oxygen. So the reason we have that is that as this stuff collapses, the heat increases, the nuclear fusion, which we'll explain in a little while, puts out a lot of energy. All right. Now, the gravity is always there trying to collapse the star even further, but the nuclear fusion in the center of the star causes the radiation pressure, which pushes out against the force of the incoming gravity. And it's totally automatic that process will eventually stabilize. Okay. And then you have a stable star. You got the radiation pressure pushing out, and the gravitational collapse pushing in. When it balances, it stabilizes, you have a stable star. Okay, so here's a little example of nuclear fusion going on. Another term for it is nucleosynthesis. Synthesis is when you take simple things and combine them to make things that are more complex. So we're taking light hydrogen atoms that you see on the left, and the pressure of the gravity forces them to combine in the process of nuclear fusion there in the center, and it puts out energy there. That energy, by the way, is in the form of gamma ray radiation. So that's, and then on the right, you see the helium atom being created by the hydrogen atoms coming together. So you create a helium atoms and you put out the energy, and that's the radiation pressure that pushes against the gravity. So that's happening in the center of the stars. So the hydrogen atom is being combined into helium. Now, helium is heavier than hydrogen. It has more protons than hydrogen does. So since the gravity never goes away, the helium atoms fall, as we described earlier, because of gravity, to the center of the star. So the core of the star is where you'll find the helium, and higher towards the surface of the star is where the hydrogen continues to exist. Okay, and so you're starting to form a layer of helium and a layer of hydrogen. All right, and there's an awful lot of hydrogen in a star, billions and billions of tons, and it can last for a long time, billions, maybe even billions of years. But there's not an infinite amount. Eventually, all that hydrogen, or enough of it, gets turned into helium. And then there's just not enough hydrogen anymore to undergo fusion. And so that fusion process stops. So the radiation pressure moving outward stops, but the gravity never goes away. So when the outward radiation stops and the gravity continues to compress, that continued compression increases the pressure more and increases the temperature more. It increases the temperature to the point where the helium atoms in the core of the star can undergo fusion. And then they start putting out the radiation pressure, it balances against the gravity, and you got a stable star again, except that you're burning helium now. So this goes on and on and on. You burn all the hydrogen, so you make helium. And you can see the hydrogen, since it's the lightest one, it's that orange layer on the top. And then the yellow one is helium, right? And then you're burning the helium, you run out of helium. When you burn the helium, when you do the fusion with the helium, you're making carbon. And then you run out of helium and you start fusing carbon, and that creates nitrogen. And that fuses to create oxygen. And and you go through this process, and you're building all of these concentric shells in the star. And eventually you're burning, the silicon is undergoing fusion. That's creating iron. And of course, iron is the heaviest of all these. As you can see, they fall to the heaviest ones fall to the center. And after a while, you run out of silicon. So that fusion stops. And you would think, oh, well, now the gravity, which never goes away, is going to increase the pressure and the temperature hot enough to start causing the iron to go into fusion. However, iron is different, and I'll be honest with you, I'm not exactly how it's different, but it is such that even if you can cause it to go into fusion, it doesn't put out energy, instead it consumes energy. Therefore, at this point, you no longer have the outward pressure from the fusion, the outward radiation pressure from the fusion. And as we said, gravity never goes away. And so what happens is, since gravity doesn't go away, the inward force of gravity starts to collapse the entire star. All the material in the star that has been burning, undergoing fusion for billions or billions of years, whatever, and the entire star collapses towards the center of its core in a matter of seconds or minutes, okay? And this, of course, is a very high rate of speed. Matter of fact, it says here, let's see, the temperatures reach billions of degrees. The collapse, all the material from the sun collapses toward the core and then bounces back. It rebounds in a big a big explosion called a supernova. All right, and just as a piece of trivia, that term supernova was first used by Walter Baade and Fritz Zwicky in 1931. These guys were ahead of their time, they're great astronomers. And so you have this big explosion called a supernova. This is a photograph of an actual remnant from a supernova. And that's what happened. Now, supernova explosions only happen with large stars. Small stars undergo the processes that we saw earlier where they create lots of different elements, okay? But you only have a supernova explosion from stars that are a lot bigger than ours. But they happen. As a matter of fact, it says here that the material is moving outwards at about 20,000 miles an hour, about 9% of the speed of light. And so as it's when the rebound occurs and the material starts to flowing out, it's even creating more powerful pressure waves that raise the temperatures, and they create lots of elements. Now, talk about supernova. I got a quick video here that just talks about supernovas for a second. Let's see here. Could you hear the music there?
We could.
Okay, I will continue it.
Astronomers have performed a great number of studies on collapsing stars, but capturing one in the optical wavelength during the early moments of explosion has proven elusive. That changed recently as scientists searching through a wealth of data gathered by the Kepler Space Telescope found what they have long been seeking. The bright flash of the shock wave, or as astronomers call it, the shock breakout, pushes outward as the distant body turned from star to supernova. Noted the lead astronomer on the team, in order to see something that happens in time scales of minutes, like a shock breakout, you want to have a camera continuously monitoring the sky. You don't know when a supernova is going to go off, and Kepler's vigilance allowed us to be a witness as the explosion began. The star was a massive one, estimated to be 500 times larger than our own sun.
Okay, so that's just a description of what happens. Here's actual photographs of supernovas. On the left, you see the galaxy. On the right, you see the same galaxy with what looks like a new star. Doesn't look like a big deal in this photograph, but it's putting out a tremendous amount of energy. That's a supernova explosion. The photograph on the bottom shows another supernova in the outskirts of a spiral galaxy. So we can actually see these things happening. Here is another photograph of another supernova, remnant, and referred to as Tycho's supernova because the astronomer Tycho actually witnessed it many, many years ago. And it is many, many times, thousands of times larger than our entire solar system. Now, this is one of those GIF videos, and if you watch closely, you'll see it slowly expands and then goes back to its smaller size. But in other words, if you look closely, you can see that we can see its expansion. Okay, as we saw earlier, 9% of it's expanding, approximately 9% of the speed of light, and we can actually see that happening. So these supernovas are happening. And here's another one, and the different colors highlight the different elements that were created in this supernova. We can see sulfur, oxygen, iron, and silicon, all the different colors that are created in the supernova. And as a matter of fact, when you ask the question, well, which elements does it create? The answer is all of them. Okay. Now, as you can see in this picture of the periodic table of elements, there's a blue stuff in the upper corners. There's the hydrogen and helium created by the Big Bang. Easy for you to say. But if you look at the color coding here, you can see that, low mass stars creates all the elements you see in yellow, exploding massive stars, all the stuff in green, and actually some of the orange stuff too. White dwarf stars exploding, which is another kind of supernova, creates all the elements that you see in blue. And then it says here, this was something newly discovered, emerging neutron stars, which are really created by supernovas. All neutron stars created by supernovas. They are responsible, along with the low mass stars, they're responsible for all that stuff you see in orange. So the processes inside stars, be they low mass, high mass, supernova, white dwarfs, they create all the elements in the periodic table. Okay, now we create a couple of those gray ones in our nuclear power plants, nuclear reactors, but all the natural occurring elements happen in the stars, And this picture kind of shows it. Now, I have now, for better or for worse, a little musical interlude that helps you understand the periodic table.
In 1869, Dmitri Mendeleev could see that properties of elements vary periodically. As atomic number increases, the properties repeat in a soothing rhythmic pattern that can form a funky beat. The elements we know about, they number 114. Some in quantities so small that they've never been seen. Most are common elements that are far and wide dispersed, but all of them together make up all the universe. Elements in group 1 are called the alkalis. They explode in water and are of very tiny size. They love to lose electrons when they form a bond. Of these reactive atoms, I can say I'm rather fond. Group 2 elements are often called alkaline earth. Calcium's been building bones since well before your birth. They form nice +2 ions and are generally quite fun, though they're not quite as reactive as the metals in group 1. Since 1869, every one of us could see that properties of elements vary periodically. As atomic number increases, the properties repeat in a soothing rhythmic pattern that can form a funky beat. Metals in groups 3 through 12 transition elements. Some of them are lightweight and others really dense. Things they have in common, they form charges 2 or more. And some form colored compounds, which is something we adore. If you want an element, just tell me once again. If it's in group 17, you've got a halogen. Non-metals so corrosive, they're not found in their pure state. They can gain electrons like they're going out of date. Got one for you in group 18, it's known as noble gas. If you're looking for an element that just sits there on its... If you wonder why and haven't figured it out yet, their valence configuration is a big stable octet. So now it should be obvious that everyone should see that properties of elements vary periodically. As atomic number increases, the properties repeat in a soothing rhythmic pattern that can form a funky beat.
Okay, everybody stop dancing now. All right, I hope you like that. Thought it was pretty clever. Anyway, so you get these supernova explosions, and they're like a dandelion flower. They do 2 things. They create all the elements, and then because they're an explosion, they throw those elements out into the universe. And so like a dandelion flower gone to seed, they are seeding the universe with all the elements, all the space between the stars. Just like a dandelion seeds your neighbor's lawns with the dandelion flowers, okay? And so after billions of years of doing this, you end up with a universe filled with gas clouds, just like at the beginning of the universe, but now these are gas clouds in space with a dust. And when I say the dust, I mean all the elements besides helium and hydrogen, okay? And just like at the beginning of the universe, those clouds are big, they have a gravitational field, they collapse, and they form new stars, okay? There's a nice picture of that right there. Now, well, that has been the theory for many, many years, but now with the great telescopes and cameras, we can actually see the stars with huge amounts of dust around the stars, all the elements outside of hydrogen. And so you end up with new stars with all of this material around the stars, and we can kind of call it leftovers. And because of a law of physics called the conservation of angular momentum, when the gas clouds collapse and the star gets created in the center. The material around the star goes into orbit around the star, as you kind of see in this picture here. A new star is born with all this dusty material filled with all the elements. Which elements? All the elements going around that star. And of course, it's a lot of material. That's gravitational field. That causes the gravitational collapse. And that's how you get planets going around a star, okay? And that's been the theory for many, many years. Now, we can actually see photographs of that happening. Up on the top, you see two photographs. The star is behind the white X and the black circle. The bright stuff around the star is infrared radiation being given off by the dust that's close to that star, infrared radiation being heat, okay? And then on the bottom, these two images are drawings that help you to visualize what the two photographs are showing. The one on the left, we can see the dust rotating around the star in this edge-on view. And then on the right, you can see the dust looking down at the disk of dust rotating around the star. So we can see that that's actually happening. And so what do you end up with? You end up with stars full of elements. And with what elements? Well, all the elements are in these generations of stars. And then you end up, well, here's another photograph that shows the iron in our sun at various temperatures. Some of the iron at 1.5 million degrees, some at 2.5 million degrees. It's showing up with these, it's color-coded. And so we know that there's iron in our sun. And matter of fact, here's another image of a sun-like star. And you can see at least three different elements in it: oxygen, nitrogen, and hydrogen. And so you end up with planets full of all the elements. Our Earth is filled with all the elements, okay? And this is just an estimate, but as it says here, it is estimated that approximately 10 supernovas and neutron star mergers were necessary to come up with all the elements that we believe are in the planet Earth. That, of course, is an estimate, okay? So as we said, the iron and all the other elements are in the Earth. The plants grow, we eat the plants, the elements end up in our body, and our bodies end up looking like this. 4 elements, oxygen, carbon, hydrogen, and nitrogen, make up 96% of our body, mostly the oxygen and hydrogen in the form of water, and then you have some other things here like sodium, potassium, sulfur, phosphorus, calcium that make up the rest of the 100%. And so and all of these atoms, of course, were created in the stars billions of years ago. And so that gets me to the fact that I learned many, many decades ago that really got me excited about astronomy. And that idea is depicted in this image here. I know this is not the real image of a nebula, but it did come from an image of a nebula that was made to look like the profile of a child face. And this image says what I learned, and that is we are made of stardust. You can't see it because of the stupid stuff at the top over there. But well, let me see if I can get rid of that here. There we go. Should have did that 20 minutes ago. Anyway, we are made of stardust. I tried to make that very obvious in the presentation here tonight. And when I learned that, it's not that we're here and space is out there. We are part of space and space is part of us. And that got me really, really interested in astronomy. And here we go. And so, as a great scientist once said, we are star children, we are made of stardust. And that's really what I wanted to show you. But in the way of an epilogue, I wanted to tell you about that iron bolt that I showed you earlier in the presentation. It's not an ordinary bolt. I'm holding it up to my camera right now. I hope you can see it. I have it here. This is a very special iron bolt for me because in 1981, my wife and I got a private tour of Kennedy Space Center. There's a picture of, we were given this tour by a NASA engineer That's the engineer and my wife. And they are standing under the Apollo 1 launch pad at Kennedy Space Center, which is where the 3 astronauts died in a space capsule test in 1967. Astronauts Chaffee, White, and Grissom. And NASA says that they are never going to get rid of this launch pad because it has become a memorial, shall we say, to those 3 astronauts. And so the NASA engineer took us everywhere at Kennedy Space Center. When I asked him, what are we going to see? He says, well, I'll take you wherever you want to go. What do you want to see? My knees actually got weak. We saw so much. But anyway, we went to go see this launch pad. And I was so emotionally gripped by just being there and how fortunate I was to be able to be there. I thought, I never want to forget it. Wouldn't it be great if I could take away a souvenir from that location? And there was this iron bolt in the launch pad. And I asked the engineer, I said, gee, would I be able to take this iron bolt as a souvenir? And he said, well, NASA sort of frowns on people taking parts of their memorials and their launch pads. But he said, and I'll never forget it, he's standing right next to me. He said, but I have to look at something over there in the other direction for a minute. And so he turned around, turned his back towards me, and I put the bolt in my pocket, and I have it here today. And I use it in every one of these presentations, which means I've used it, 20, 25 times. I've given this presentation in one form or another. So because of that, because of what this iron bolt is, I consider it significant because the iron in this bolt was created by stars billions of years ago. And then in the Apollo program, we used that iron that was created in the stars to send a whole bunch of iron back to the stars in the American space program and the Apollo program. And I kind of consider that an interesting aspect of cosmic recirculation, So that's what I mostly wanted to tell you. I thank you very much for your time and your attention. And so that's one of the big reasons why I'm interested in studying astronomy for so darn long. And I'm ready for questions, any comments, if there are any.
Great presentation. Thank you so much for that, Bill. That was absolutely wonderful. We did have one question in the chat, and that was Chris Morissette. Chris, do you want to come off of mute and ask your question to Bill?
Yeah, thanks, Joe. Yeah, Bill, really good presentation. Could you talk about how elements heavier than iron are actually created? Is it the explosion forging heavier elements from the material that had been burned in the star, or what exactly is going on?
Okay, darn good question. I say it's a good question because I asked the same one myself several years ago. I had the fortunate experience to spend some time with a scientist whose job is to study supernovas. Okay, I don't remember if he was NASA or not, or worked at a university. I think he was NASA. But anyway, I was able to ask him that question, and the answer from him. Now, you know how things always change in science, right? I'm constantly having to update this presentation because of that. So things change. But what he told me then, and what I've since been able to confirm as far as I can, is that the elements are created at 2 times. One, when the collapse occurs. When the collapse occurs, tremendous amount of pressure. The temperatures go up to over 1 billion degrees, I think a couple billion degrees. And with those kinds of temperatures, you can create anything, all right? Anything gets created. You can create it. However, the temperatures and pressures are so great that this is what he told me, that all the stuff that was created in the stars for millions or maybe billions of years gets blasted apart. So all that work kind of has occurred for naught, perhaps, maybe not all of it, but at least some of it. But then you get the supernova explosion, and then the material is all flying outward at, well, you can imagine, well, we already said it, at a decent percentage of the speed of light, which means, again, the pressure waves going through all that material from the star, tremendous pressure, and they again increase the temperatures to billions of degrees. and create all the elements again. And then at those two times, at the collapse at the core and at the outward pressure waves through all that stellar material, those are the times when all the elements get created. Now, you probably saw in the periodic table neutron star mergers too. All right? Similar situation, high pressures and temperatures. And of course, where you get neutron stars from supernovas. But that's pretty much my answer to your question. I hope that answers your question, or is there more?
No, it kind of confirms. Well, my thought was that the explosion is acting kind of like a reactor, you'd say find in a chemical plant or something like that. And I think that's the way I understand it. I think that's what you're saying. So, no, that's great.
A little different than a nuclear reactor, but I believe that the result is the same.
Yeah, I mean, like a chemical plant, chemical reactor. You put heat and pressure on some material, and you get something different out at the other end.
Oh, bingo! Heat and pressure, absolutely.
Yeah. Okay. Thank you.
No, you're welcome. Thank you. Great question.
Yeah, great question.
As I said, it's a great question because I asked it too.
I'd asked it at one point as well, and I was told that essentially at those pressures and those temperatures, you end up with a neutron soup. I think I'd read somewhere where a star that's 25 times the mass of the sun, when it goes supernova, there could be temperatures of up to 10 billion Kelvin.
There you go.
As a result of that. So, temperatures that extreme, it goes well beyond our conventional understanding of chemistry and physics.
Yeah,
right?
No, absolutely. Are you saying that possibly it's actually hotter than Southeast Texas? Is that what you're saying?
Barely, but without the humidity, it's a dry heat.
Yeah, I bet it is.
All right. We had another question in the chat. Universe EQ Earth. Do you want to come off of mute and ask your question? And if not, I can ask it. And then I'm trying to understand the question. It says, what's the role of asteroids in creation? And I'm wondering if that's in the creation of stars, or, if you are here.
My question is about in the creation of these planets and everything.
Got you.
I'm sorry, I didn't quite get that. Are we asking what is the role of asteroids in creation? Was that the question?
Yep, role of asteroids in the creation of planets.
Oh, well, we were talking about stars here tonight. However, we did talk about the creation of the planets too, planet Earth, etc., and the other is with the elements. And there is no doubt that in those pictures that I showed early in the presentation, I'm going to try to bring, this one right over here, you see the star being created. I don't know, can you see this picture still?
Yes.
Okay, you see the star, the new star created in the center, and you can see the planets rotating around the star. And those planets, you might be able to tell they look very hot. They're probably all molten material. And there's two basic reasons why the planets are molten. One is there's a lot of radioactive elements in them, and that's causing them to heat up. But two, you have the material in that rotating cloud going around of material going around the star, and it's falling on the planets, and that of course is going to be include asteroids, and they are falling into the planets, causing the planets to heat up and become molten. And of course, the planets are going to take millions of years to cool down, but a lot of that material falling into the planets is going to be what we would normally call asteroids. And so that is the role, I think, I hope I'm answering this correctly, that the asteroids play in planetary formation.
Yeah,
I hope that answers your question.
Yeah, thanks, Bill.
Well, you're welcome. Thank you.
Okay. We have another question from Salil Kulkarni. Salil, do you want to come off of mute and ask your question to Bill?
Yeah, thanks a lot, Bill. This was an excellent presentation.
You're welcome. Thank you.
Yeah, my question was that the original at the beginning of the universe, as you mentioned, it was mostly hydrogen, maybe some helium, and I understand that we've gone through some number of some number of generation of stars already at this point. Do we have an estimate of what percent of the universe is now metals, heavier elements, or is it still primarily hydrogen and helium?
I'll bet you the answer is yes, but I ain't got it. Okay. I love that question. I'd love to know the answer. I'll bet you there's some smart guy out there. I'm writing a note down right now, boy, Doug, because that's the percentage of metals. You're talking about the whole universe? Oh,
Yes,
man.
Well, Bill, I'm not smart, but I read ahead and I did look this up.
Yes.
And so according to Lawrence Berkeley National Laboratory, 73% of the mass of the visible universe is in the form of hydrogen, which is lower than I thought it might be. I thought it would be higher than that. So 73% of the visible universe is hydrogen. Helium makes up about 25% of the mass, and everything else represents about 2%.
Wow.
So, wait a minute, you went fast. So you're saying the metals is 2%?
The metals is 2%. That's right.
2%, yeah.
2%. Okay. Well, I hate to break it to you, but what we have learned recently, I know you have, is that the percentage of the universe that's so-called visible material
Yes.
is pitifully small.
That's right.
Pitifully
Yes.
small, yes.
So is the dark matter metals or not? Don't know. Okay. If you can find out, there's a Nobel Prize sitting on a shelf in Sweden right now, just waiting for you. But of the visible matter, only 2%. I'm shocked. I would have bet. I had money in my pocket. I was going to bet more. But you know what? There's a lot of hydrogen out there.
There's a lot of free floating. That's why I thought it would be higher than 73%. But yeah.
A lot of hydrogen. Anyway, what was the name of that lady astronomer who figured out stars are made of hydrogen? I forgot her name, Polish name. But anyway, a lot of hydrogen out there. And so, okay. Thank you for reading ahead. You get extra credit, Joe.
I only did it on this one. The next one's a tough question. So Rupal Vyas, I hope I pronounced your name correctly, had a question. Do you want Rupal to come off of mute and ask your question?
Sure. It's Bill, excellent presentation. The question I have for you is, at what point the nuclear reaction starts and the star is born, right? So all the dust starts falling into its center. At what point it ignites and a star is born?
Okay. Well, the shorter answer is it's different in different stars. The core of our star is believed to be somewhere around 10 to 15 billion, 10 to 15 million degrees in the core of our star. However, we know that there are stars that are much hotter. We know there are stars that are much cooler. We have things like the red stars are much cooler than our star. And then there's brown dwarfs. Are those stars? Well, yeah, I suppose. And they're much cooler. So the short answer has got to be, I don't know. They're different in different stars, but I'm thinking, 100,000 degrees isn't going to cut it. You're going to have to be a couple million degrees, I think, to be called a star. But right now, I can't tell you any better number than that. Again, different stars have different temperatures.
Yeah. And again, kind of looking ahead, for hydrogen to fuse into helium, 13 to 15 million Kelvin.
There you go. Okay.
Oh, wow.
And then when you get from helium to carbon and oxygen, it's a much greater temperature. You're looking at 100 million Kelvin at that point. So
that's yeah.
Yeah. So the heavier the elements, the more temperature and pressure. And again, like Bill said, it's dependent on temperature, pressure, different variables that go into it. Absolutely.
Several million. Yeah. And that's almost as hot as El Paso.
But it does give you an idea to reach those temperatures, what the density of that mass needs to be, right?
The pressure, just by gravitational pressure and nothing else.
Yep.
Causing it to heat up. Man, oh man. Yeah.
Yeah. Okay. Blanca had a question as well. Blanca, do you want to come off of mute and ask your question? Maybe not, but her question.
Sure, I'm
there
sorry.
you go. Yeah, no worries.
Okay. Yes, I mean, I understand all the elements coming from the stars getting to the Earth, but how it came to be part of our bodies. So,
well, for instance, let's just take one element, the element of iron, created in the stars, becomes part of planet Earth. The plants grow in the ground, and another word for the ground is planet Earth. And when the plants grow, they take the elements up out of the ground, literally. Okay, they feed on these elements that are in the ground. They become part of the plant. They become part of the fruit or vegetable that grows on the plant, or the grain. Right? We eat them, and then they're in our blood. The iron's in our blood, and there's a lot of details that go into things like how do we metabolize our food and stuff like that. But that is basically it, from star to planet to plant to food to us.
But what I meant is that without the iron, we don't have blood cells. So it had to be a part that, of course, we get it from what we eat, but we were born with blood cells, so we have iron already. So what I meant is how to become part of that iron, if there is any mechanism that we adapt so we can survive, because we have to have the iron to have cells, blood cells. Yes. Or.
Well, you said we had the iron when we're born. That can only mean one thing. We got that iron from our mother. Okay, period. Okay, and mom is able to make that iron because she eats the food that grows on planet Earth. But if you're asking me, how did the first creatures have blood and iron, and how did the life form to be like that? I am not authorized or.
Okay. Yes.
Hey, Bill, I can tell you. Life has been using iron way back, because all the genes involved with moving iron around and stuff are like widely shared across like the whole kingdom of plants and animals.
Yes.
It's like a really, really early development.
Yes. And it started with very, very simple creatures, obviously. And then it became, the creatures evolved into astronomers, okay? The most advanced creatures that exist. But, you're talking about a non-astronomy topic, but nonetheless a very important and interesting one. But you're talking about biology and the evolution of living creatures in our biological environment. And doggone it, I wish I knew the details of that. Another Nobel Prize is waiting for that answer. I'll tell you that. And I'm afraid that's about all I can tell you. I wish I could answer it better.
Mm-hmm. And I was wondering also how, because the percentage of hydrogen is higher than any other element in the universe, and we're not really, our main percentage is hydrogen. So to me, that is kind of interesting.
Right.
Yes.
Yeah, we're less than 10%.
Thank you.
We're less than 10% hydrogen, even though it's the most abundant material out in the universe, right?
Yeah. Is that what it was? I forget my diagram.
Something to that effect. Yeah, I can't.
Let's see. Hydrogen. It said hydrogen 9.5%. Very good, Joe.
Yeah. I was paying attention.
He takes notes.
I was paying attention.
Thank you.
Absolutely. All right. I appreciate the question. These are really tough questions, Bill. I mean, you're getting some things that really are, like you said, if you can answer these, you would have multiple Nobel Prizes. So
yes, these are tough questions, but as I stated in the beginning, that's my payment, Joe.
That is absolutely.
Absolutely.
All right. And Abdi Canales had two questions. Abdi, do you want to come off of mute and ask your questions? Okay, said no, but I'll go ahead and yeah, no worries. I'll go ahead and ask them for you. So Abdi's first question was, why are the planets closer to the sun rocky, but the ones farther away gassy?
Oh, forget about it. Holy mackerel. 50 years ago, we had the answer to that question. Okay. we said, well, it's pretty obvious. It's colder out there. You're going to have the elements like hydrogen and helium making up the gas giants out far away. It's too hot near the sun. All those lighter elements are going to be boiled away by the sun. So you're going to end up with rocky planets close to the sun, gas giants away from the sun. And whenever we find planets on other stars, it's going to be just like that because boy, it makes so much sense. Then 5,000 planets later that we found now, almost none of them are like that. Okay?
Hot Jupiters, right? Yes. Yeah,
et cetera, et cetera. And so, boy, can we get stuff wrong sometimes. But, that's science, man. If you want to get like write a science textbook and expect it to never change, good luck. The stuff changes every 20 minutes. That's just the way it is in our solar system, and we have found that it is not the way it is in other solar systems. And I haven't heard anybody say, "Here's how solar systems form" in that context. Okay, they haven't written that chapter of the book yet, so we're just beginning to learn.
Yeah, no, that's a great point, Bill. Like you said, 50 years ago, it was believed that the rocky planets formed closer because the heat of the sun would condense the rocks and metals, and you wouldn't be left with much gas, and that's why you got the rocky planets there. And then, like you said, and then of course further out you would be able to escape some of that influence. Obviously, the influence of the sun gravitationally is pretty large, but get it far enough away to where you could have more of those gases and whatnot accrue around an object, and you'd have these larger bodies. But there are several theories out there. There's some that say that actually Jupiter and Saturn formed much closer and eventually migrated out. As Bill said, many of these exoplanets that are being discovered are many times the mass of Jupiter and are found at closer distances from its star than even Venus is and Mercury in some cases, right? So it's still a mystery. There's no telling why. What we thought were conventional knowledge about the development of planets and solar systems and things like that have been completely upended. So that's all still being learned. That's a great question. And then the second question Abdi had was, does that mean that living beings are entropy reduction machines? Man, you're getting all the great ones, Bill.
Yeah. Well, it's getting kind of hot in here. Entropy reduction machines. Well, yeah, I like to think that I do a little bit more on a given day than that, but that's one of the things that we do. Okay, we change the level of complexity in our own bodies. However, I can't really say anything more than that. I don't know. Are you trying to make me feel big or small by asking? I'm not sure. So I can't. I don't think I can add too much more than that. I mean, that's one of the things that a living creature does, but I think we do a little bit more than that.
Yeah. Well, Bill, you're getting paid a lot with these questions tonight.
Yes, I am. Hey, by the way, I got to show you something. I've been joking about the Nobel Prizes, right? I went and visited the Nobel Prize Museum, and I think it was in Sweden, or was it Norway? It was in one of those two places.
Oslo, I believe it is. Or
yeah, like you said. And I said, what a great souvenir would be? You got little like phony plastic Nobel Prizes. And they went, oh, no. We don't make those because, and then they came right out and said they're afraid that people would, tell others that they're real, that the guy really won a Nobel Prize. And they absolutely positively don't want that to be happening. But they sold little chocolates. I don't know if you can see this on the screen or not.
Yes.
This is a chocolate covered with gold foil that looks just like a Nobel Prize.
Very nice.
So all I can promise is that if you answer some of these questions, I am going to be there to give you one of these, and you'll have your own phony chocolate Nobel Prize.
Wonderful. All right. Does anybody else have any questions of Bill? That was everything that we had in the chat. If you do, feel free to come off of mute and ask away. We've got time for another question or two.
I got to be in bed by 11, but other than that, I got plenty of time.
Yeah. I was going to share. I saw that there is an ISS pass that's supposed to be really nice tonight around 8:45. I'll double check what time it is, but shortly and maybe half hour after this meeting, that we were supposed to get a really nice ISS pass. I think they said it's going to last about 6 minutes. I'll look that up here in just a bit. But the other thing I wanted to share, Bill, was that we're putting together an amateur astronomy 101 type course that's going to go for a few hours over 2 days. So for members of the Houston Astronomical Society, you want to learn how to use a telescope, what the differences in eyepieces are, differences in mounts, how to set up a telescope, things like that. We are in the process of putting that together. So hopefully we'll have something in the next few months, and anybody who's interested in that course can join us. So that's what I have to share.
May I ask one more question here?
Please.
What is the farthest observation we have made from the Big Bang? So is it 200 million, 300 million years old? What is the oldest observation?
The oldest observation. I think by that you're meaning what is the oldest object we've seen?
We see stars and galaxies and so forth, and we know that they are 4.5 billion years old or 5 billion years old. What is the oldest object that we have seen?
I believe I'm correct in saying, and I am certain there is other people on the line right now who could help me with this, that the Webb telescope, being able to see in the infrared, can see things much further out in the universe than anything else, I believe. And we are now seeing galaxies that we're seeing the image of the galaxy as they existed a mere couple of 100 million years after the Big Bang. And so I believe that would qualify the way you're asking the question for the oldest thing we've seen. So these things are several billion years old.
Yeah, it's one of the. Oh, go ahead. I'm sorry.
So 13.8 minus 0.2, right? So about 13.7.
Right.
Or 13.6 rather. Yeah. Okay.
Something. Yeah. Give or take 100 million years. But who's counting? Something like that.
Who's counting? That's right.
Well, and that's really kind of one of the main purposes of the Webb Space Telescope is to kind of be able to peer that far back. I know there was a galaxy candidate that was observed by the James Webb Space Telescope. They believe was formed about 230-ish million years after the Big Bang, right? The estimated timeline of the Big Bang. So that's the furthest back that they've been able to see thus far.
Yeah, I've been made a liar in the past, but I'll say it's hard to imagine seeing something older than that.
Yeah,
but we'll see.
Exactly. I have a feeling we'll come back in a year or two and say, you know what? Remember how foolish we were when we said that, right?
Yeah, we used to be. It's just like teenagers, that they were so smart when they were younger.
Yeah. All right. Well, Bill, thank you so much for the wonderful presentation. This was absolutely. It's always fascinating, right? When we get back into cosmological origin and how things are formed and how they contribute to what makes us what we are today. So this is really, really wonderful. I appreciate it. And it sounds like a lot of people got a wonderful education out of it as well. So thank you, Bill.
So one of the reasons why I study astronomy, man, I'll tell you.
Yeah, it's absolutely, you never stop learning. And what you learn today may not necessarily be true in a year or so, right? So
you are correct.
We're always learning. So thank you again, Bill. That was absolutely wonderful. So
you're welcome. My pleasure.
All right. Well, I'll let everybody else get out to take a look at the ISS pass. Like I said, it should be happening around 8:45 p.m. this evening, but you might want to Google search that and double check the exact times. But I also wanted to let everybody know, and thanks to the vote, everybody today, that our next meetings are going to be September 7th for our novice meeting and September 8th for the general meeting. So not the first Friday, but the second Friday of the month. So please join us for those. We'll send information about the speakers and how to get registered in a few weeks. If you have any questions about the club, want to find out what's going on, see what events we have going on, you go to our website, astronomyhouston.org. And if you're on any of these social media sites, and I guess I need to change the icon for Twitter there, I call it X now. But if you're on any of those social media platforms, please give us a follow, see what's happening there. And lastly, if you have any questions for us, give us an email, info@astronomyhouston.org. We love receiving emails and hopefully answering those. So thank you again, everybody, for joining us tonight. Thank you again, Bill, for the wonderful presentation. Everybody stay safe. Go take a look at the ISS, and hopefully you enjoy some of this dry weather to get out and do some observing. So take care, everyone.